be placed on its INT stand. The technician is now preparing the satellite for the installation of the solar arrays, and here you see one of the wings being installed on the satellite. Shortly after that was completed, a release test was performed, and here you see the wings being moved as they will be released on orbit. Now a technician is preparing the communications antenna for installation to the observatory, and here you see them installing it on the aft end of the spacecraft. Here the technicians are preparing the flight sunshades for the star trackers. These prevent sun from causing glint into the three spacecraft star trackers. Cleanliness is important. Here a technician is using a black light to clean any particles off the spacecraft prior to fueling. Now the spacecraft is being prepared to be transported to the hazardous processing facility. It's been double bagged, and it'll travel about 100 yards to a facility where the hydrazine is loaded. Following fueling, the satellite was lifted, and you'll see it mated to a gray structure. This is the interface adapter that will sit on the launch vehicle. Now it's time to bring the satellite to the launch pad. The ULA transport container is lowered over the observatory. You'll see it put on the trailer, on which it'll be transported out to the pad. And finally, it begins the long drive from the Astrotech facility out to the launch pad. And here you see it arriving with the lights of the gantry behind the spacecraft. If we could go back to the graphics. Here you see a beautiful picture of the GLAST Observatory sitting on the second stage of the launch vehicle. The first half of the fairing has been installed onto the launch vehicle. Next slide. And in just a few days, here's what we hope to see on orbit. The solar array will be deployed. The communication antenna will be deployed. Over the next 2 weeks, the mission operations team will be checking out the satellite, the spacecraft. At that point, the two instruments will be turned on. Over the next 6 weeks, those instruments will be calibrated and checked out. And at that point, we'll turn it over to the science team, and they'll begin their journey and exploration of the high-energy universe. Turn it back to George.
All right. Thank you, Kevin. And now for the science that GLAST will be performing. Dr. Stephen Ritz, the GLAST project scientist and astrophysicist from the Goddard Space Flight Center. Steve?
Thanks, George, and good afternoon, everyone. We have a new observatory with breakthrough capabilities ready to launch just a few kilometers away from here, and it's about to open up the universe to us in new and very exciting ways. There's a broad worldwide science community that's anxiously awaiting the launch, and we're just incredibly excited about it. Before I get started, I'd like to emphasize that we're here representing a worldwide team. There are a few people here I would like to point out who are here with us and are also available at the end to answer any questions you might have. First of all, I'd like to introduce Rob Pinkerton from the General Dynamics GLAST management team. Sitting next to him is Professor Lynn Kaminsky from Sonoma State University. She's the GLAST press officer. Next to Lynn is Dr. Lori Leschen, who is the Deputy Director at Goddard Space Flight Center. Next to Lori is Dr. Julie McHenry, one of my colleagues. She is a GLAST Deputy Project Scientist, an extremely active member throughout all aspects of GLAST. And sitting next to Julie is Professor Peter Michelson from Stanford University. Peter Michelson is the Large Area Telescope Principal Investigator and is one of the prime movers of the GLAST mission. There are other people who are unable to join us here today, particularly from our international collaboration. We just simply wouldn't be here without them. You already heard from Kevin Grady some of the many contributions that they've made. Somebody else who's very important, who's unable to join us today, is Professor William Atwood from the University of California, Santa Cruz. Bill is the principal architect of the GLAST Large Area Telescope and indeed of many other key aspects of the mission. So why are we here and why are we so excited about looking at the universe in gamma rays? Well, throughout all of human existence, there's been a shared and common experience of looking up at the night sky at the stars. And we've had, I think, an abiding sense that there's something important to figure out. But it's only very recently in human existence that we've come to understand that all that light that we see is actually indirect or secondary emission from fundamental physics processes that are actually happening at much higher energies. For example, at the core of a star, there are nuclear processes injecting energy into the star, and that energy slowly makes its way out of the star, and we see it as visible light, light at the star, at the surface of the star. But what we've come to understand is that we need to look at higher energies, and following that trail of what's really going on has caused us to look in other parts of the electromagnetic spectrum, as John Morse had talked about before. So could I have the first graphic, please? So here you see a graphic of the electromagnetic spectrum, and right in the middle of it is the wavelengths of electromagnetic waves that compose what we call visible light, the light that we can see with our own eyes, and the different colors just correspond to different wavelengths. But as you go down to the longer wavelengths to the left, you see radio waves and microwaves and infrared, and I think that's quite familiar to people. As you go up to shorter and shorter wavelengths, you go again through visible to ultraviolet, then to X-rays, and finally on to gamma rays. Now, just as you know that the water in which you swim, the waves at the beach, are actually not continuous, but in fact composed of little bits or molecules, the light that we see is also composed of little bits, little packets of energy, and those are called photons. And the energy of each photon is directly related to the wavelength of the light. The shorter